Distinguishing among atoms. Elements differ because of the number of protons. This is called the atomic number. If you look on the periodic table, elements are arranged in order of increasing atomic number. For example, hydrogen is number 1, which means hydrogen has 1 proton. Helium is number 2 atomic number, which means it has 2 protons, and so forth. Elements are arranged by atomic number, the number of protons in the nucleus. The mass number is the number of protons and neutrons. The mass number is not given on the periodic table, but if I want to find the number of neutrons, I take the mass number and subtract the atomic number. We'll look at shorthand notation, which uses the mass and atomic numbers. I'll give you some examples of shorthand notation. It will look something like this, where the bottom number is the atomic number. The top number is the mass number. So from this, I can determine the number of protons, electrons, and neutrons. The number of protons is 9 because it's atomic number 9. The number of electrons is also 9 because this is a neutral atom. Now the number of neutrons, we're going to take the mass number minus the atomic number. So 19 minus 9 to give me a total of 10 neutrons. Okay, let's work the other way. If I tell you the number of protons, electrons, and neutrons, you should be able to write shorthand notation. So it's number 56. So you look on the periodic table, you find number 56, and the symbol is Ba, which is barium. So there's my atomic number, 56. It's neutral. It's got 56 electrons. It's got 81 neutrons. So the top number up here would be 56, which is number of protons, plus 81. So that's going to give me 137 for the mass number. So that would be the shorthand notation for that isotope of barium. Isotopes are atoms with the same number of protons, different number of neutrons, so they have different masses. There are 3 known isotopes of hydrogen, for example. Hydrogen, which has 0 neutrons, would have a shorthand notation that looks like this. Deuterium has 1 neutron, so its shorthand notation would look like this. And then tritium has 2 neutrons, so its shorthand would look like this. Now these are the isotopes of hydrogen. They're all alike because they have 1 proton. The difference is the number of neutrons, but that doesn't affect the chemical reactions of hydrogen. So these are all alike because they have 1 proton. Ions have lost or gained an electron. They have a charge. Here are some examples of some ions in shorthand notation. 3517 Cl minus. The number of protons, electrons, neutrons. Well, the protons is 17 because it's chlorine. It's number 17. The number of electrons, if it were neutral, would be 17, but it's not neutral. It has a negative charge. Well, protons are positive. Electrons are negative. So if I have an overall negative charge, that means I have to have 1 more electron. So 18 electrons. The number of neutrons is 35 minus 17, mass number minus atomic number. So we have 18 neutrons for this ion. Let's look at another example. 2713 Al plus 3. Number of protons, electrons, neutrons. Well, protons, bottom number, 13. That's easy. Aluminum is number 13. 13 protons. Electrons. Overall, it's got a positive 3 charge. Well, protons are positive. Electrons are negative. If overall it's positive 3, that means there have to be more protons. 3 more protons in this case. So 10 electrons. The number of neutrons is mass number minus atomic number. 27 minus 13, 14 neutrons. So those are ions. They have a charge. And if there's a charge, it'll be over here in the top right of the symbol. Atomic mass is the weighted average mass of the naturally occurring isotopes. These numbers are on the periodic table. Hydrogen, for example, has an atomic mass of 1.0078 AMUs, which stands for atomic mass units. But these numbers right here, these atomic masses, these decimal numbers, those are on the periodic table, along with your atomic number. Boron has two isotopes, boron 10 and boron 11, which is more abundant if the atomic mass is 10.81. Well, if the atomic mass is closer to 11, that means in terms of abundance, there has to be more boron 11 that occurs naturally. So boron 11 is more abundant in nature. To determine the atomic mass, the decimal numbers that are on the periodic table, you multiply the mass of each isotope by its abundance, and then you add the products. So let me go through an example with sulfur. I want to find the atomic mass of sulfur. I'm given all of the data. Sulfur has 4 isotopes. So what I'm going to do is take the mass of each isotope. I'll start with sulfur 32, which has a mass of 31.972. Multiply by its abundance. It's 95%. I'm going to change that to a decimal, so 0.95002. I'm going to do that for the sulfur 33, the next isotope. Mass 32.971 times its abundance in a decimal, 0.0076. And the next two as well, just the mass times the abundance. And I just carry out about 4 decimal places. It really doesn't matter. But I'm carrying out 4 decimal places in these. Okay, so I multiply the mass times the abundance. I want to calculate the atomic mass of sulfur. Those are all the isotopes, the 4 isotopes. I simply add these 4 numbers together, and I'm going to get the atomic mass. Now the thing is, if I'm calculating atomic mass, I already know the answer. It's on the periodic table. When I add those 4 together, this is what I get, 32.063 by adding these 4 numbers here together. And that should be relatively close to what's shown on the periodic table. So that is how we calculate atomic mass. So atomic number, number of protons, and atomic mass are shown on the periodic table. So on the periodic table, I've already mentioned elements are listed in order of increasing atomic number. There are 7 periods, 7 rows on the periodic table, and properties of elements vary as you go from left to right. Groups are columns, and you will find elements with similar chemical behaviors in a column. For example, if you're in column 1A, lithium, sodium, potassium, they have similar chemical behaviors.